up to the ideas that we have been talking about this week. And yeah, so that's what I'll be trying to work. And this is related to this, what's generally referred to as spin momentum locking. And the idea is that, and it applies to many different types of materials. So narrow gap semiconductors like indium arsenide, topological insulators. So these are cases where the conduction channel is at the surface. So in any solid, it's like at the surface conduction. And here the surface conductors are believed to have this kind of a spin orbit coupling term. And what this term does is, it produces this spin momentum locking. That is, the eigenstates have a specific relationship between E and sigma. So spins, so if you are traveling in a certain direction, so if you are talking of electrons going in this direction, then the eigenstates are the spins that are in the direction of z cross p, like we were discussing yesterday, because each electron feels an effective magnetic field in that direction. So the z cross p is, so this is the direction of, this is the surface, electrons are moving in this direction, z is the perpendicular to the surface, so z cross p could be in this direction. So that's the up and reverse is the down. And those are the two eigenstates. Now, in the case of heavy metals, that is tantalum, platinum, etc., that's where also people see very similar effects. So we'll be talking about the general results we'll be talking about, I believe, in some cases have been observed and in some cases have not yet been observed. But my feeling is it should be generally applicable to all these groups of materials. And these are surface conductors, whereas these are generally bulk conductors. In the sense, it's a wire of tantalum, for example. But what people see is, of course, that the current, that if you have a charge current flowing this way, it produces a spin voltage at the surface, or a spin current if you put something, if you put a conductor on top. And so from outside, it's basically the same phenomenon. Now, in these cases, people think there may be some other bulk mechanism involved, and that part's still being debated. But we could understand the basic phenomena in terms of this basic picture that I'll be trying to tell you about. Now, the structure we'll be talking about looks like what I have drawn there. So you have those yellow contacts are normal contacts. You've got these two yellow contacts, and those two contacts that are blue, those are the magnetic contacts. So magnetic contacts could be pointing, and the direction of the magnetic contacts is perpendicular to this plane. So that's the direction of the spins, the eigenspins. Right? But because those magnetic contacts are intended to detect those spins, so they will be in that direction. And the basic result I'll be talking about. So let me just state what, at the end of the lecture, I hope I'll be convincing you of that. But let me just state what talk about, and that is this, that if you take a structure like this and measure the four-terminal resistance, it means you run a current here and look at the voltage between those. So that's what I've written as R1, 2, 3, 4. So run a current between 1 and 2, look at the voltage between 3 and 4. And the way, and this is the basic result I'll be trying to convince you where it comes from, etc., is this. That supposing in the beginning, both magnets, let's say, are in a particular direction, which I'll denote by blue. Then as you gradually increase the magnetic field, in the end, they will both become red. That is, go the other way. They'll all get flipped. But generally, in these experiments, the way that people do it is, they make one magnet have a slightly lower coercivity than the other. So that as you run the magnetic field, it switches before the other one. So, as you turn up the magnetic field, of course nothing happens as long as it's negative, but once it's positive, then one magnet turns red a little earlier than the other one. So in this region, one is blue, one is red. And by blue and red I mean a magnet pointing into this plane and perpendicular to this plane. And then when you turn up the magnetic field more, they both become red. And the thing is that here, this is the original resistance in the sense voltage divided by that current. And when they are anti-parallel, it goes up here, and then it again comes back down. Now, if we go the other way, again, as you turn it, this one, the right-hand one flips first, so it becomes blue, and then it goes back here. Now, the surprising thing in this so those are the kind of, so this is both blue, then it's blue and red, and then this both red. But then when coming back, this is reversed, red and blue. So the overall the point to note is that in these regions you would call it a parallel configuration, that is both blue, both red. These are anti-parallel, one blue, one red, but here it's red, blue, here is blue, red. And the surprising thing is, that's what I want to convince you, is that the resistance is not the same. So the two anti-parallel configurations have different resistances. That's the surprising point. And this is, I think, what we predict was the prediction. And now there is, I know of one published experimental result that actually shows this in tantalum. And there's another group working on indium arsenide who I also believe have seen this, but I think it's not published yet. Okay? So I think this is right, and I want to convince you why. Okay? And of course, offhand your question is, how do I know the difference between red, blue, and blue, red? And the answer is, of course, this is where the spin momentum locking comes into this story. That ordinary conductors, anti-parallel is anti-parallel. It really doesn't matter whether the anti-parallel is red, blue, or blue, red. You should get the same resistance ordinarily. But because these materials has the spin momentum locking, there is a directional difference. And so it makes a difference. So ordinarily what would have happened is you would have seen something like that. That's the picture you normally expect. That anti-parallel, high resistance, parallel, low resistance. That's the basic GMR type style thing we've been talking about. The surprising thing is this. And one point let me even state right now, is that this is also what we predict you should see if you do a two-terminal measurement. What I mean is, this is what you will see if you run the current here and measure the voltage there. If you run the current here and measure the voltage right there, then you would actually get that curve. So that's 1, 2, 1, 2, whereas this is 1, 2, 3, 4. Okay. So that's basically what I'll be trying to convince you in the next 40 minutes or so. Okay. So we start with, if you think if any conductor, not necessarily one of the spin momentum locked conductor, anything, you apply a voltage across it, and notice the structure I was showing you earlier, these. I was running the current here and looking at the voltage there. But for this discussion, let's reverse the voltage and current terminals and just run the current through the outer ones, and we'll connect up. But let's start there. So when you look at the electrochemical potential, when you apply a voltage, general thinking is it will go linearly from this value to this value. But one of the things I've been trying to convince you, I guess this week we have been talking about this mesoscopic physics result, that in ballistic conductors, actually it doesn't go linearly like that, rather it's flat, mu plus and mu minus, separated. And when you have a diffusive conductor, the correct picture is really more like this, where you have a mu plus that's sloping down, mu minus, but they're separated. And in general, current flow means this is bigger than that. And what you can show is that this part, this is like the separation between mu plus and mu minus. And compared to the total voltage, that ratio is like in the ratio of length of the conductor to the mean free path. So current can be written as the difference mu plus minus mu minus times this ballistic conductance. And one point I want to make is that even in a diffusive conductor, that relation is still true. That is, although it's ballistic conductance times that, but it doesn't mean it needs to be a ballistic conductor. In other words, if you have a non-ballistic conductor like this, then this mu plus minus mu minus, which is this separation, it is a fraction of the total voltage. So the total voltage is this one. That's the full thing. And mu plus minus mu minus, that's like a fraction of that. And the fraction is mean free path divided by length plus mean free path. So the actual conductance is this much. It is less than the ballistic conductance. But the first relation is still true. That is, if you just relate the current to the difference between the mu's, then it's still always ballistic conductance. It doesn't matter. Because basically the current is proportional to this separation. Doesn't matter how long you make it, that separation stays there. For a given current, you have that separation. Okay? That's one point I want to stress. And from this you can, so here I'm just kind of restating the things we did earlier this week. So it's just standard mesoscopic physics still. I've not brought in anything new so far. And so from this you could say, okay, what is conductance? It's current divided by voltage, and that is like this ballistic conductance times mean free path. That's like your conductivity. And then is this, I guess this would be L plus lambda in general, but if it's a long conductor, you can drop the mean free path and just write it length. And this is what I would say is this Kubo formula that we had mentioned, that conductivity is like density of states times diffusion coefficient, and that's the diffusion coefficient. So this is all standard, applies to any material, but the viewpoint though is inspired by mesoscopic physics. So how do you connect this up? Well, the point is we are talking about materials where you have spin momentum locking. What that means is that ideally it's almost like any state going to the right has a up spin. And of course, when I say up, what we mean is spin going to the right has a spin in this direction. Any electron state that goes to the right has a spin this way. If the electron is going to the left, the spin is the other way. So what that means is that you can associate, ideally, all up spins go to the right, down spins go to the left, and so you can associate mu plus with mu up, mu minus with mu down. Now, how can you measure this? Well, that's where this idea of using magnets comes in. That if you have a magnet that is in the direction of the up spin, then what will happen is it will have a relatively low resistance connection to this point and a very high resistance connection to this. So the way I think of it is, you've got a mu plus and a mu minus. And when I bring in a probe, this a resistance like this. So let us say this is very high. I guess if I'm trying to measure this, then I'll make this relatively low. So I'm just putting some arbitrary numbers. Like this is 1 ohm, this is 1 mega ohm. Then the voltage you'll get here will be more like this one. In general, it will be divided in that ratio, basically, because no current can flow out. So, because these are high resistance probes, no current flows out, but this will adapt a voltage such that whatever current flows here kind of comes back there. And that determines this potential, and it will be relatively close to the low resistance side. So bottom line is, if you have a red magnet, ideally it will measure this one. Blue magnet, ideally will measure that one. And so, you could write the voltage measured here outside. This is actual charge voltage. You have a probe that floats to some potential, this probe floats to some potential, look at that voltage. That voltage will be equal to V0, which is just the fact that there's a slope here, so the potential here is different from this one. That's the V0. But then a little more, because on the right hand side I'm measuring that one rather than this one. So if both had been red, I'd have got V0. But because one is blue, I'm getting that one. And one is blue and one is red. That's why it's V0 plus a little bit. And how much extra? Well, it's this I over GE. Because it's this mu plus minus mu minus. That's it. Now, so what I wrote down is like the basic result. There's a couple of factors that come in when you take into account some of the details. One of the details is that I said an electron moving this way has a spin like this, and my magnet, if it points this way, it only measures that way. But then all electrons aren't going straight. Some of them are going like this. If it's going like this, the spin is like this. And if the magnet is in this direction, you don't quite get this one, but there's a cosine theta factor that comes in. Anyway, so bottom line is that when you average it out, that cosine theta over all the angles, that's how you get the 2 over pi. Another factor that comes in is that, again, real materials, it's not like everybody going to the right is upspin, everybody going to the left is downspin. There's also some downspins going to the right, some upspins going to the left. It's just that ideally this would have been 0, but in general, this is m, that's n, m greater than n. And so, that would also reduce that effect somewhat, because whatever this gives, this one kind of gives the negative of that. So you're getting, so it will subtract from that. So overall what will happen is, the effect will get reduced by a factor, which we write as small p. And what is that small p? It's this m minus n over n plus n in this thing. This tells you how many of one type compared to the other.
So it will depend on degree of polarization of this.
Degree of polarization of the channel. So it's a channel property.
Channel.
Degree of spin, momentum, locking, etc. And if it was a normal channel, no spin orbit coupling, small p would be 0. Effect would be 1. And one last thing is that the magnets aren't perfect. So even when you have a red magnet, it sees both the red and the blue, just that it's closer to the red. Because, ideally, this resistance is 0, that one is infinity. But in practice, of course, they're not exactly like. So what you get is reduced by a factor that depends on the polarization of the magnet. Okay, so that's the basic result there. So this is what we had predicted, that's like 5 years ago actually, that in that paper, this was the basic result we had put down. And since then there's been a lot of experiments which have confirmed this basic picture. So this is an experiment from 2014, and I think you can kind of see the structure. So this is bismuth selenide. You're running the current in this direction. That's 3,4. That's the 3,4. And then in between you have the 1 and 2. And of course here I drew the 1 and 2 kind of along the current flow, but it's actually put perpendicular to the current flow, which is nice because then the V0 sort of goes away. Because the V0 came from the being along that current path. Okay, drop along the current path. And you'll notice this is a magnet that's covalent. So one of them is a magnetic contact, the other is a normal contact. And I think what they saw was, this is straight from this paper. So you have a magnetic field, and what the magnetic field does is switches this magnet. And this so current is flowing this way. The magnet, so magnets usually have this easy axis, the direction of magnetization, which is usually the long direction. So if you have something long like this would be the easy axis, not this. So here, the magnets are, easy axis is this way, which is the direction of the spins that we should, because current is flowing this way, so that's the direction of the spin you should expect. So as you turn up the magnet, I guess when the magnet switches, goes over, and again when you change the magnetic field, it comes back. And if you reverse the direction of the current, reverses. Right? That way. And I think that paper also showed angular dependence. That is, if they force the magnet to not be along this or this, but something in between, how the voltage changed. So that also, I think, followed the expected pattern.
Is this room temperature?
No, this I think is low temperature, 4 Kelvin. If I remember right, 4 or maybe 10. Low temperature. And since then, as I said, there's been a lot of papers. I think one of them may be room temperature. I don't remember which one. So there have been a lot of papers which have seen this basic thing, this basic result. So this, I think, is fairly well established. Looks like basic thing is there. And you see it follows in a very simple way from what we have been discussing most of this week. This idea of mu plus and mu minus. Basically it's mu plus and mu minus, which became mu up and mu down. And magnets give you a very convenient way of measuring mu up and mu down. Because the fact that mu plus and mu minus will be separated, that is part of mesoscopic physics. We have kind of known it a long time, but it's always very hard to measure them individually. So it has always been one of those things that's kind of in the theory, but not something you can easily probe experimentally. But what's different now is, or what I really liked about this was, that got translated into spin, mu up and mu down, and magnets give you a natural way of measuring it. Okay. Now, what I want to talk about though is a slightly different structure, which is where you run the current here and look at the voltage there. So that's different from what we just discussed. What we discussed is running the current here and voltage is inside. But the thing is, those two things are connected by this very general principle of reciprocity, at least for linear response. One thing to remember is, when you go away from linear response, reciprocity may not hold. It does not hold. But as long as you're doing low bias linear response measurements, this is a very powerful principle. The idea that, I think Butiker used it like 30 years ago, and that's a seminal paper from 1986. Probably there's thousands of citations. And he used that to explain this magnetoresistance of small conductors. And the basic idea being that, that's.
Just before you say, can I go back to previous? I don't know what is the.
Yeah, sure.
What is the NGO layer it's doing here?
That's an oxide, right?
Yeah.
So I'm wondering whether it has.
Because that will be a tunneling barrier, right?
Right. So yeah, this is one interesting point I should come back to, and that is that the way I made the argument, it works best if you have a relatively high resistance contacts here. Because I said that you have a mu plus and a mu minus. Mu plus and a mu minus, and some probe comes in and measures this resistance. Now it works best if this is a high resistance, so it doesn't perturb or change completely what you are measuring. Whereas if it's a low resistance contact, it will change things somewhat. So in general, it's better to have an insulator here, but what we have now understand is that depending on the conductivity of this channel, this requirement may or may not be very stringent. But I think here they did it this way because I guess they wanted to have a relatively high resistance contact. So that it's more like a potentiometric measurement in that sense. Okay? So this idea of reciprocity, as I said, Buttiker used this 30 years ago, and it was a very powerful method. The idea being that if you take any structure in the linear response regime, if you run a current, measure the voltage, run a current through 3 and 4, measure the voltage at 1 and 2, the answer is the same as if you run the same current here and look at the voltage there. And I guess there is one subtlety to that. I'll come to that in a minute. And this point, I think, has been, I think that paper itself also checked it. There is a this is a 2015 paper which did that, where they interchanged. So one case you are running the current this way looking at the voltage, another you are running the current here looking at the voltage. They actually checked this reciprocity also. So, and one little subtlety is that when you apply the basic reciprocity relation is what I've written there. That Rijkl equals RKLij. If you interchange current and voltage terminals, it's the same resistance. But one subtlety is all magnetic fields and magnetization type of things should be reversed. So this is again one of those things that involves this time reversal arguments. So actually this and this wouldn't correspond. What would correspond to that is this one, in the sense that I reverse the voltage and current terminals, but I should also reverse the magnet. Red should become blue. And that is reflected in a minus sign. But that is one subtlety involved. You have to also reverse the magnet in order to apply reciprocity. But magnitude-wise, of course, this is it. And one point to note is that if you are doing a two-terminal measurements, two-terminal meaning Ij and KL are the same one. So you are looking R12, 12. Then the thing is, you should get, you see, then Ij, KL is same as KL, Ij. Then basically it tells you that if I reverse the magnets, nothing should change. So whether it's red or blue, if I just measure this two-terminal thing, there should not be any change at all. But four-terminal, there will be a difference. Now, oh, sorry, I went the wrong way. Yeah. Now I just want to say a few words about this resistance, about the white oxide here. So the thing is, you see, you're considering two types of situations. One is when you run the current here and you measure the voltage there. The other one is when you're running the current here and measuring the voltage there. And what reciprocity tells you is that those should give you the same answer. But when you think of this one, it looks like it shouldn't matter too much whether this is a high resistance contact or a low resistance contact. And after all, I'm just running this current in here. and looking at the voltage. And the way you think in this case is you say, this is a magnet, so when I run a current, actually there's a spin current that is injected, and I get a voltage that's because of the inverse spin Hall effect. That's how you interpret that. Whereas this one is more like running a current, and as a result I'm getting a voltage here, which can drive a spin current, etc. So it's kind of like spin Hall and inverse spin Hall, or I think in the 2D conductors they call that the inverse Rashba-Edelstein effect. But in my mind, I think they're all kind of basically the same thing. But when you look at this structure, I think it looks like you need high resistance contacts. Because remember, the way I argued is when you run a current, you separate mu plus and mu minus. And then there is this magnet which measures it. Now, if this magnet happens to be a very low resistance thing, then you see there will be a lot of these upspins going in, coming back in, etc. And it would change what you're trying to measure. And when you actually do a full numerical calculation, what we have found is that in general, how much of an effect you get, you could quantify with a quantity like this. That is, supposing you're running a certain current here, one way to quantify the interface resistance is to say that, let's say I ground this, so I short this, then if I have 1 milliamp flowing here, how much of that 1 milliamp will flow out from here? If it's a very low resistance content, then most of it will flow out. And then you'd be more on this side. And then the effect is reduced significantly. So generally what we have found with the detailed numerical calculations is that you get a strong effect, relatively strong effect, as long as the current that is flowing here, not much of it is diverted into that one. So if you actually shorted it, how much of the 1 milliamp would go away there? That's a very good measure of things. And as long as that's small, you're okay. And this is the factor that I feel makes a difference between, I say there's all these different semiconductors and metals, which will all have the same basic phenomena. But this is the point that makes a difference there, in the sense that if this is a metal like tantalum, then even a relatively low resistance contact does not divert much of the current. On the other hand, if this is a high resistance semiconductor, then the same contact resistance could divert a lot of it. So, on tantalum, you usually with normal contacts, even without NGO, you tend to be here. Whereas in bismuth selenide or indium arsenide, unless you have an insulator, you might end up here and lose the effect. That's what it is. And that seems to be what I'm also seeing experimentally, what I'm hearing from experimentalists also. Okay. Now, let me just spend a couple of slides connecting up to a different kind of experiment that people have done. And this is this is a paper where they reported results on, I think this was copper bismuth, CuBi. So copper with bismuth in it, bismuth doped copper. And the experiments were done with the spin pumping experiments, which means they are injecting a spin current there, which is like a magnet, hit it with AC, means the magnet precess, and in the process it injects spin currents. And they measure the voltage across the terminal. Now, of course, we have been talking about contacts, and what I would argue is that you could take something like that and conceptually replace it with two magnets, a blue one and a red one, through which you run a current. Because then what would happen is that there is minus Is over 2 flowing here, and the spin current would be reversed here, and it would effectively give you the same thing. So that's the real experiment. This is what I'm saying, conceptually you could replace it that way. As if you have two magnets and you're running a current through it. So here you're injecting blue spins, here you're pulling out reds. But the spin current is in the same direction, so the two add up and effectively give you that. So that's just a conceptual equivalent. And why am I drawing this? Because once I have this, I know how to draw the reciprocal. And the reciprocal would be, here you are running a current, measuring the voltage. Here you run the current here and measure the voltage here. And this, of course, is the basic experiment I started with before. Whenever you run a current, there's a nu plus and nu minus that's separated, gives you a spin voltage, so we know exactly what that will be. So that would be, so the voltage you get here would be related to this spin current through this relation, and this is exactly what we had like in the very first, when we were talking about the experiment with current flowing and difference between mu plus, mu minus, etc. 2 over pi due to angular averaging, P due to the polarization of the channel, etc. And what is usually measured in these experiments though is not the open circuit voltage, but rather the short circuit current. And that short circuit current would be like this voltage, I guess, times the conductance of the channel. And that would give you, so the parameter that people measure in these experiments, this is called this inverse Rashba-Edelstein effect, IR. And the parameter people measure, from this point of view, you can see in just 2 lines, you get that answer. It depends on this spin momentum locking of the channel, that's measured by this P that I mentioned before, which is m minus n over n plus n in my mind, and the mean free path that comes in. And this agrees with, so this is what we got from what I'm discussing today. What this paper had was an expression that looked like this, where this was alpha r is this coefficient of the spin orbit term, and there was a spin scattering time over h bar. This is the expression in this paper, and what I can show is they are equivalent, because given the Rashba Hamiltonian, you can calculate P, which is m minus n over m plus n, which is like this, k1 minus k2 over k1 plus k2. Those are the k's of the 2 Fermi surfaces that go with it. And so from there, you can make the connection that this is really like that. But it gives you a very different way of thinking about the whole problem. That's what I'm thinking. And if you, yes.
This lambda is for speed, right? Not for charge current.
The lambda?
Yeah.
No, it's the mean free path, the usual mean free path. In what I am doing, this is usual mean free path.
Because this tau is
Yeah,
for speed.
very good point. So this looks like spin, right? So, but in this paper, I think it wasn't clear what this represents, which time. Because this was just intended as a heuristic thing and wasn't quite settled what it should be. But you're right, that's an issue. Because I'm using the lambda, which is here. And so in these materials, I'd say from the numbers they quoted, it looked like the spin momentum locking factor was like 5% or so, m minus n over n plus n. Lambdas of about 20 nanometers, which correspond to the kind of numbers they were getting. Okay. So this is a bit of a detour in the sense that everything else we are talking about is with electrical contacts, whereas these experiments are usually all done with spin pumping. And the way I'm connecting it is by saying spin pumping is conceptually equivalent to doing something like this with perfect magnets. Perfect meaning whose P magnet is 1. And once I have this, then I can use reciprocity arguments to convert it to the problem I know how to do from mesoscopic physics. And that's the overall.
This sample is Bismuth of copper, right?
It is Bismuth group.
So this lambda is not too high for that. It's 29, it's a very low temperature.
These are low temperature measurements. So in bismuth group copper, you would have expected lower numbers, right? Yeah. So there, just from the data, I think this is the solid number. This part is we are guessing from other
Because
things.
the product, P could be high.
Could be higher, right? This part you are trying to guess based on other things, based on what alpha r might be and so on. So it's roughly right, but in detail I don't know. Okay, so getting back to regular contacts again. As I say, basic idea, Previously it was, we're running a current and we had one magnetic contact, one non-magnetic contact. Now let's say we put two magnetic contacts. So one measures this, one measures that. Then if you had both blue magnets, then what would happen is they would measure this and this, which is, let's say, V0. If you have both red magnets, you measure this and this, which is also V0. So that's why both blue, both red, they both give you V0. If there's one red and one blue, like I've shown here, then you see you're measuring a little more, because this is red, this is blue, so measuring V0 and a little more. So that's this V0 plus a little more. But if you reverse it, then you measure a little less, because then this is blue, so here you measure this one and that one is measuring that one. So it's reversed. So that is why you can see that in these structures, those two will give you V0, this will give you more, this will give you less. That's clear. And now I'm going to invoke reciprocity again. So reciprocity arguments would be, okay, that's the top one. The reciprocal structure is what's on the right hand side. Of course, whenever you do reciprocity, reds have to become blue also. Right? So reverse it. But now I'm running the current through the inner magnets and looking at the voltage outside. Next, the blue, when I reverse, it's two reds. And this is red blue, when I reverse it becomes blue red. Blue red becomes red blue. This will be the overall. So now you'll notice that you kind of are getting to what I said in the beginning I was trying to show you. That what's up there, those two are these parallel spin belt, parallel configuration, both blue or both red. And what you are predicting is you get the same voltage for both. But these are anti-parallel, but the key point is this is anti-parallel and that is anti-parallel, but the voltage is different for the two. And so the corresponding resistance is also different. That's the argument. And the other point I stressed earlier also, that this whole reciprocity, when applied to 4-terminal devices, it gives this. But in terms of 2-terminal devices, it basically says that if you reverse magnetization, you'll always measure the same resistance. Because R1212 plus M is R1212 minus M. So as long as you are measuring 2-terminal things, it doesn't matter how you reverse magnets, you should all be. Now, so reciprocity gives you this argument. The part that we have tried to, what comes out when we actually do the numerical calculations is in detail why the potentials are the way they are. Because here I'm kind of invoking reciprocity. So the argument is something like, but this requires more discussion, and that is that inside there is this slope, but at the ends, depending on whether it's blue-red or red-red, etc., the end potentials can be different, which means if it is say if both are blue, then the end potentials would be here. Whereas if both are red, at the ends it would be here. Whereas if it's red and blue, it would be these two or those two. That's kind of what happens. But that part needs more discussion to see why. But the clearest, the most convincing argument is really the reciprocity. And that then leads to this basic picture that I started with. And yeah, this is in a paper that came out earlier this year. So I just took this picture out of that paper actually. And then just to regarding the numerical method that we actually use to model this, that's why let me just mention that you see the basic diffusion equation is this d mu dx equal to the current. That's the standard diffusion equation. Now in mesoscopic physics, this separation and all that requires an equation that looks something like this, where you have a d dx of mu plus and a d dx of, this one should have been mu minus. And all these equations, of course, are derived from Boltzmann equation with the right assumptions. So this is what's in mesoscopic physics. And one of the points I try to stress in general is how important it is to think in terms of electrochemical potentials. But that's already happening in spintronics because people have different potentials for mu up and mu down. And the Rutherford equation you'll see a lot in the spintronics literature, where you have mu up and mu down. That's this equation up there. And in order to do the kinds of things I discussed here, you kind of need to combine the two. So what we have is a set of equations that actually has mu up plus, a mu down up minus, and a mu down plus, and a mu down minus. So there's kind of 4 electrochemical potentials. That is what we use. So if you're actually interested in details, yeah, those are in the papers that we didn't go through. But numerically, when we calculate it, that's the kind of equation we have actually been using. So let me just quickly summarize then. What I've been trying to give you is this, a different perspective on this whole problem, which is inspired by mesoscopic physics. And of course, these 2 equations we have been talking about in much of this week. The new concept here is that m can be different from n. And that is, there can be a difference between how many ups are going to the right compared to how many downs are going to the right. And that is the measure of spin momentum locking. Right? And that parameter then can be used to understand a lot of these properties. And because one thing I try to stress when talking about mesoscopic physics is that one of the most important concepts to come out of all this is this concept of number of modes or number of channels. So, and this is a quote from Phil Anderson. I think this is a book that came out a few years ago, that out of that whole localization theory, it's like one important concept that came out of all of that is that when you think of low frequency conduction, you can think in terms of these channels, right? Channels or modes as they call it. Right? And this is kind of an attempt to use that same concept to understand spin momentum locking. Okay. I think, yeah, that's it. Thank you.
Take some questions now.
Sure.
No questions? Then let me ask, so is this the only method by which you can determine the chemical potential profile in a diffusive conductor? I don't think of any other method.
So, of course, for all of these are semi-classical thinking, so generally it's a starting point should be Boltzmann equation. Right? And the various diffusion equations are things that come from Boltzmann equation, but with appropriate assumptions along the way. Right? So I would say that, so usually that's the usual diffusion equation everyone uses. In the context of spintronics, people are now using Rutherford equation. That's the spin diffusion equation. In the case of mesoscopic physics, this difference between mu plus and mu minus. And what I'm saying is in this high spin orbit material, you kind of need about 4 chemical potentials to do it. Okay? And what's interesting about, what I feel makes all this more real. So this, in mesoscopic physics, I think has been generally known for some time. But what makes this a little hard to verify experimentally is that this mu plus and mu minus are not easy to measure. So it is kind of always in the theories, but you cannot really look at it.
This is one of the way.
Right. Because mu up and mu down are readily measured nowadays. Because magnets allow you to measure one of them compared to the other. Because you can make a contact that only sees up or only sees down. The part that you wouldn't come out of, is hard for other things. So that I think has been very useful in terms of understanding what goes on inside.
If you replace this cobalt with half metal, then your P will be quite high, right? So suppose you change that blue and red with two half metals. One is spin down, one is spin up.
In the theory, I think I have these two P's there. Go back to the beginning. Yeah. Or maybe one of these. So there is two P's. One is the small p and the other is the capital P. So the capital P is the magnet property. That is where you want a good magnet. The small p is a channel property. So it is this m minus n over n plus n, not related to the magnet.
Oh, yeah, this is in the channel.
This is the channel.
Yeah.
So what you measure involves both. So if this was just an ordinary channel like copper, then the small p is 0.
Yeah, but then your P will be much different with one potential already. If the channel is not improved, you improve only the spin injection, so D will remain same.
So for the same channel, you'll get much better results with that one. So I think, yeah, this one looks like they were using cobalt iron boride. And with the insulator because they want a high resistance. And this is Ti. That's one of the structures that was used. The other structure I remember is this one. So this is cobalt.
Cobalt is used because it has probably the highest spin polarization of all three. Iron, nickel, cobalt.
Sir,
Please.
is there any reason to measure the transverse magnet resistance? This one is measuring transverse one, right?
In this direction. Because the way I think is it removes the V0 from the story. Although you could, what I mean by that is, the way I'm thinking is this picture. So the V0 comes from this drop. And the second term is this separation, which is the actual physics. So if you could put the red and the blue almost at the same point on the current path, then you get rid of the V0. So by going this way, you are kind of putting them at the same point on the current path. That's my case. But experimentally, I'm not sure they were necessarily thinking this way. It is probably the most convenient thing to do at that. But this then at least minimizes the V0.
Yeah, but take probably it's possible to do 6 bolts. So one you can take along and then across and see whether you can sense the VG.
Right.
5 contacts.
So what was the typical channel width here in experiment?
Channel widths. See if they had a picture, I'm not sure. I'm not sure. I had guessed my few microns, but I'm not sure. Okay. I'm guessing tens of microns, but I don't remember.
So you said in tantalum, in addition to the surface mineral, something also in the bulk may be responding. What is that?
Because a lot of so this is where they make a, so the same basic effect, when you see it in a surface conductor, you call it the Rashba-Edelstein effect. When you see it in a bulk conductor, you call it spin-Hall effect. And in people's mind, those are two very different things. But in the context of tantalum also, now I think there are papers which are arguing that this is also a surface thing. That at the surface you basically have a Rashba conductor anyway. That is, I've seen arguments. On the other hand, most of the classic theory of spin-Hall effect involved saying that you have this material with scatterers inside, and the scatterers. So if you have a conductor with a scatterer here, and this is in the bulk, that's the surface. So ordinarily you would say the scatterer should not want to turn you one way or the other, except that the scatterer in a material with high spin orbit coupling could have this property of turning you more one way or the other. And so there's a lot of literature on those things,
Yeah.
this skew scattering and side jump and all that, which has to do with these bulk-like issues. That whether in a high spin orbit material, just scattering processes can do this. Whereas what I described to you is basically a surface theory. And as I said, the different categories of materials I mentioned in the beginning, these are basically surface material, surface conductors. This one is not. So this is where it's, and as I said, there is evidence, or people are arguing that this is also what you're seeing is really a surface effect, but that's not a settled question.
But there are some papers which shows that a scatterer can give rise to this kind of polarization.
Can give rise. So a lot.
Parallelizing oxide in this system.
So it could be bulk effect.
Bulk.
And the general thinking always was this was all bulk effect and these are surface, which is why I say people would call this Rashba-Edelstein effect, call that spin-Hall effect. So externally the fact is the same. You run a charge current, you get a spin current this way. The experimental fact is the same. You are measuring it at the surface. You're really seeing the same thing.
No other question. So, okay, let us thank Mr. Datta for an thought-provoking Let us break for tea, and we can reassemble here around 11:30. Is that okay?